Hi, I'm Jamie Cannon. I'm currently a student at UNLV for spring 2021 semester, currently enrolled in AE 221L, and this is my final project, the 3-bit analog to digital converter. So a 3-bit analog to digital converter is designed to take an analog signal or voltage and produce a digital output. And by converting from the analog world to the digital world, we can begin to use electronics to interface to the analog world around us. The number of binary digits or bits used to represent this analog voltage depends on the resolution of the converter. And on the bottom there, I have different sensors that take an analog signal and turn it into a binary output. And then this is my block diagram that I designed. So it takes a voltage and divides it up with a voltage divider. And at each one of these nodes, after each voltage drop, the voltages are going to be different. And these are going to be the outputs of the voltage divider, and which will be the inputs to the encoder. Inside this encoder, I have these comparators here, these op amps. And these comparators, depending on what voltages are applied, will compare the two voltages, and depending on how they're applied, will either allow a voltage to pass through or not. So for example, if a voltage is applied here that is higher than the voltage that is applied here, then it'll allow this voltage to pass through. If this voltage is less than the voltage that is applied here, then this voltage will not be allowed to pass through at all. And VDD would be located here. This is the voltage that will be allowed to pass through, and VP is the voltage connected to the positive node, and VN is the voltage that is connected to the negative nodes. And the outputs to the priority encoder end up being LEDs 0 through 2, so the 3 LEDs that represent the 3-bit binary output. And then, so the first thing I did was I created this schematic over here. I know you can't see it because my face is in the way, but I started with the schematic. I created it in Microsoft OneNote, but I started with this voltage divider. So I took 5 volts, divided it up in between 9 1K ohm resistors, and after each voltage drop, there's a different voltage found at each of these nodes. So the first one would be 4.4 volts, 3.88, 3.32, 2.76, and so on. And those voltages are all connected to the negative terminal, and those are what you're comparing to. So you apply a voltage here at VP. Those are connected to the positive terminals of each comparator. And depending on if this voltage that you're applying is greater than the voltage here found at VN, if it is greater, then it'll equal 1, which just means that this voltage is allowed to pass through. So for example, the first node here would be 4.44 volts connected to the negative terminal. And if you apply a 4.5 volts to the positive terminal, because VP is greater than VN, it'll allow this voltage to pass through. And then if you look, if I were to have applied a 4 volt voltage instead of a 4.5 volts, because VP is less than VN, a 0 would be applied, which just means that this voltage does not pass through. And after I did that, I used these tables to do this, and I created a truth table and made it all nice and neat. And so it's looking to see if these values are applied, a 0, 0, 0 will be outputted in LEDs, and if these values are applied, a 1, 1, 1 will be outputted to the LEDs. This is a priority encoder, which just means that the leftmost value takes priority over the rightmost values. So because a 1 is found here, it doesn't matter what the rest are. If these are 1s or 0s, it doesn't matter. It just all matters about the leftmost digit. So if D6 is 1, it does not matter what the rest are. So the first one matters, of course. but it all matters about which one a 1 is applied at. And so VP, I chose between values of 1 volt to 4.5 volts, incrementing every half a volt. VDD is 6 volts, and then VN, like I said before, is 5 volts, and that's divided up between these resistors. And then from this truth table, I took the 1 values for each of the outputs and found their expressions for each one, and I continued on. So once I had the expressions, I was able to actually create the actual encoder part. So for expression for LED2 would be this, and that's just 3 OR gates put together, connected to these values, these comparators. So I did that for all 3. Like the second one has 3 OR gates and 2 AND gates. I connected them as well. So I know I could have simplified these further, I think a little bit, but I was fine with the AND and OR gates only. So then I connected everything together in one large schematic, one basic schematic that shows the voltage divider, the comparators, and the encoding part, and connected everything together, and then transferred it over to LT Spice, exactly the same as how I have it here. So it all transferred over to LT Spice. For the comparators, I had to Google which one to use because LT Spice has many different variations of everything. So I ended up using the LT1720 as a comparator and connected all that. The OR gates and the AND gates were all 4 input AND and OR gates. So instead of connecting four of them, I still connected only 2 so that it matches my schematic better that I originally created. And then I simplified the truth table so that you can see what value of VP you apply here to get what output for the LEDs. And so yeah, I then do a demonstration. So for my demonstration, I started with showing if you apply a 1 volt voltage at VP, you should get 000 out of it. So I created everything in LT Spice and connected all of those for the graphs, and then I click run, and I end up getting 000 out of it. And then I move on to the next voltage, 1.5 volts for the VP, and I should output 001. So then 1.5 volts, I click run, and I get 001 as it should be. And then I do it again for 2 volts. With 2 volts, I should get 010 out of it. So I change that to 2 volts, click run, and I get 010 out of it. And so in reality, I guess this voltage right here, you can vary it with a potentiometer or some other device, I guess. And you can vary your voltage to change the LEDs to what you need them to be. So yeah, it runs, everything works perfectly. All the voltages have all the correct outputs as I expected, and it was very fun to do. So the main challenge that I had when doing this was just really understanding what a comparator is and how that type of op amp is used, because I never have come across that exactly, because we've used op amps in our classes before, but never in this manner. So it was fun learning about that and actually designing my own encoder like this. I wanted to do it in hardware, but I didn't have the material to do it with, so simulated was just as good though for learning. But yeah, it all works last one right here, 4.5 volts, should give me 111, and it does, 111. So yeah, that was my demonstration. And this was my presentation for the 3-bit analog to digital converter. I'm Jamie Cannon. Thank you for watching.